we go. Okay, so so yesterday we looked at the jet clustering more or less and features about that, but it's time to now look sort of inside the jets that have substructure. So I showed you this this image yesterday. So you have a dijet event. Well, this is actually a TT bar event. I didn't tell you that. It's pretty likely to be a TT bar event. This is in data, so it's something like 95% purity or something. So this is almost certainly a top quark. So you have a very large radius jet over here, and if you look carefully, you can kind of see that there are three bumps within that jet that correspond to the B to K plus the W to QQ. It's the same on the other side, but probably a little less clear. So we call these things subjets. They're areas of activity that are within the jet. So if you're looking at a single jet, you can have a single particle, and that has a 4-vector, right? That being said, the next simplest thing is to add a gluon, like we talked about yesterday, and that gives us the simplest next to leading order observable of a jet, which is the jet mass. There are others, obviously, but this is the one that's kinematically related. It's a kinematic variable, so it's the other one besides the PT that we're interested in, obviously eta and phi as well. But what the jet mass is just the vector sum of all the particles that are inside of it, and you take the invariant mass. That's it. If you do this with, for QCD, the average value of m squared is proportional to PT squared times r squared, and the proportionality is alpha with the Casimir factor CF or CA, depending on whether the progenitor is a quark or a gluon. And a very important piece to remember is that this has an enormous number of gluons, as we talked about yesterday, with varying probabilities, and you have to resum them all in order to get to understand what is actually happening. So this leads to a so-called to a divergence as mass goes to zero. But so you would, if you look at this, this is the differential cross section of dijet events with respect to jet mass without any grooming applied, which we're going to talk about soon. You can see the data here in black, and you can see a couple of Monte Carlo predictions here with varying degrees of accuracy. We're not terribly concerned with the disagreement here in the vertical direction, because this is the absolute differential cross section. So as you've been hearing, there are a lot of uncertainties for the PT spectrum of dijet events. It sounds pretty straightforward, right? But it's actually kind of challenging to get this right to better than a factor of 2. So the fact that these all kind of agree, this depends on the PDF choice, on the distribution functions you use for that, plus a bunch of other stuff. But at the end of the day, what you see is a suppression of that exponentiated spectrum because the phase space is getting restricted very strongly, and that's called Sudakov suppression. So what you see is this peak-like behavior here. So we're going to come back to that in a little bit. So aside from just being fun and an interesting application of QCD, why do we actually care about looking inside of jets? Mostly because we're trying to distinguish QCD jets originated from a quark or gluon from something that's more, let's say, interesting for BSM physics or other electroweak physics or things like that. And that is to classify boosted particles that decay hadronically. For a long time, we thought that this was just totally hopeless. And when I was a young lad at the Tevatron, this was just something we couldn't do. We just couldn't. But the idea is that if you have some heavy particles, suppose you have a top quark that will, maybe irradiate a gluon or something, but then it will decay into a B and a W, and the W will go to a lepton neutrino or 2 quarks or whatever, and the B quark will possibly radiate. And so you have a bunch of intrinsic centers of radiation that are going to depend on the intrinsic mass of the particle. On the other hand, if you have the other category, so you just have a gluon jet or something, and a gluon splits to gluons and gluons and gluons and quarks and gluons, there is no intrinsic mass. I mean, the quarks have a small intrinsic mass, but it's much, much, much smaller than the mass that's generated by QCD for the jet itself. But there are so many scales here. I mean, for top quarks, there's actually two mass scales here that are not present in QCD. So we should really be able to distinguish them, and we can. But the idea is that we need to understand what's happening over here for the QCD radiation in order to distinguish it between something that's more lumpy in structure, let's say. So there's lots of ways to investigate the difference between heavy decays into jets and quark or gluon-initiated jets. The first one is to look at individual prongs, and you're kind of doing that by eye, right? You say, 1, 2, 3, there's something happening here. And that's kind of what we loosely refer to this as prong finding. And you look for well-separated parts within the jet and try to identify them that way. There's also radiation constraints. You can look for more or less radiation in the jet, and more radiation means it gets wider and therefore increases its mass. So you can do that as well. And not only that, you can also look at grooming, and you select parts of the jet that you find more interesting than others, and say, well, maybe this part is bad and these 3 parts are good and this part is bad, and we want to do an analysis there. And of course, these are all extremely related, and so one is going to play into the other, and you use grooming and radiation constraints to do prong finding very often. Okay, so these are interconnected features that you can use to your advantage. So this started really picking up in the mid-aughts and the early 20 teens, and this is just a picture of just a snapshot of, let's say roughly 10 years ago, of what the explosion of tools that happened. I'm going to go over a few of these. Again, this is a slide from Gavin Salam. This is just, we stopped updating this because it just is exponentiated. So there's so many tools that it's hard to keep track. But at the end of the day, we're going to take a look at just a few of them. So we're going to go through first classification of boosted jets. I did get a request to talk about quarks and gluons, which I threw in a few slides at the end. So if I skip a little bit of material to get to that, it's because somebody asked. So I will try to get to everything, but I only have an hour, so I'm gonna try to get through it all. All right. So if we look at our picture, we have 2 categories. One that's heavy particles decaying into jets, and the other is light particles decaying into jets, like quarks or gluons, and like quarks or gluons. So if you look at the mass of something that's heavy and gets boosted, it's very different from the scale of QCD radiation. So the W's and Z's are 80, 90, or 125 for the Higgs, and the top is about 173 GeV. And then there's also extensive differences in the particle content. They often decay to B quarks, which is good because B quarks have a lifetime, and lifetime can be identified by the experiments. So that's extremely important. And they also have a shape that's substantively different. It's either 2 or 3 pronged, depending on what you're looking at. So it could be Higgs to BB bar, which is 2 pronged, or Z to BB bar, or Z to something, 2 prongs. Top quarks to B plus W can be 3 prongs. On the other hand, QCD is basically driven, all the mass is driven by radiation. There is no intrinsic mass to speak of. Up and down quarks are effectively massless, right? The particle content can have B quarks. Sometimes you get gluons that split into BB bar or CC bar, but sometimes they do, but most of the time they don't. And it's also normally 1 pronged. And so it looks like, kind of a big blob and occasional radiation. So these are all things that these are handles that we can use to do the classification. The first thing is if you have the mass, you can classify this by grooming away the soft radiation, because that will eliminate most of the mass of most QCD jets. So that's the biggest tool we're going to be able to deal with, is using the mass and the width of the jet. You can also classify this with displaced particles for any different particle content. It works much better for the category A than category B, just because category B has so many fewer of them. And also you can classify by the shape. So all 3 of these kinds of things can be used in conjunction. And at this point in life, we're using machine learning and AI algorithms that are combining all this information together. But I think it's much more instructive to start going through this, and instead of just screaming at ChatGPT to write you an essay, right? The point is to write the essay. You need to understand the material in order to do this. So we're going to go through this. I'm not really going to talk about the machine learning part. It's throw it all together into a blender, stir it up, and out comes normally some classification decision. But we actually need to know what's going into the blender. So We talked about yesterday about the anti-KT algorithm and how it's basically an idealized cone algorithm. You have some tower, it's very massive, you draw a circle around it, and that's the jet, right? And anti-KT more or less does that as it is, so you can kind of just psychologically think of it that way as a heuristic shortcut. But the question is this picture okay for boosted topologies? So in order to do that, we need to do a little bit of math, but I promise this isn't so hard. So even I can do this as an experimentalist. So if you have some particle that is moving and it has some energy E and momentum P, and has a mass that's not zero, suppose that decays into two other particles, P1 and P2, that are not massive. So think about this as like Z going to QQ bar, instead of Z to say mu mu. Or so this also could be Z to mu mu as well. This also applies. So what we're interested in is this angle between them. So we're going to make a few simplifying assumptions. So if you just look at the invariant mass of the states, the mass of this particle is m squared, of course. And if you do the expansion here, you just get a couple of approximations. If the constituents here 1 and 2 are massless, we can just say that m squared is approximately twice E1, E2 times 1 minus the cosine of the angle between them. Now, if you assume that both of the particles have equal energy sharing, which is pretty close to accurate, you say E1 is equal to E2 is equal to the original energy over 2, then m squared looks like E squared times 1 minus cosine of theta 1, 2. So if I rearrange this in terms of cosine theta, which is the interesting part, you can see that this is 1 minus m squared over E squared. Okay, bless you, which is 1 minus 1 over gamma squared. So if you do an expansion of cosine theta and you just identify that this is 1 minus theta squared, you can see that that is, therefore, theta 1, 2 is equal to 2 over gamma. So for a long time, if you just remembered this was enough to make you a boosted topology expert. You just say, oh, wait, no, that's going to be, you could just magically pull out a number if you figured out what the mass was, and you go look at the PT and you're like, oh, yes, no, the angle is pi over 2. And it would be like a magic trick that you could do this. And you just have to remember this one simple formula. And everybody was like, oh, you know things. I'm like, yes, I know. Give me a faculty position, please. It's a little harder now. I'm sorry, guys. So the moral of the story is, however, as you get more and more boosted, it becomes smaller and smaller angles. When I was a graduate student, we were talking about this, but in the context of like pion decays. And I was talking about this with some of the undergraduates at the institution I was at, and they were baffled that this could be true. They're like, wait a minute, what do you mean? The angle is constrained? I'm like, yes. Because kinematics, it's right here. But it is slightly counterintuitive, but if you kind of think about it, it more or less makes sense, right? If you have a fireworks display, if it's not moving, it just kind of explodes and goes all in the same direction. If your firework has some momentum, all the fireworks are going to go in the same direction. So the angle ends up being inversely proportional to gamma. So what does that mean? There is a problem. Because if you have an R that you picked for a jet algorithm, it's going to be wrong. Doesn't matter what the R that you picked. Because if you look at this, theta is like 2 over gamma. So if you picked, let's say R is 0.5, if you want them to be in separate jets, the distance has to be greater than 0.5. And so that means that you actually put a maximum energy cut. Not great. Don't do that. That means that the requirement is that the energy of your jet is going to be always less than 4 times the mass. So if you wanted to look at like a 1 TeV Higgs boson decay, you would not reconstruct it correctly. Not great, right? We like to keep our highest energy events, so we need to do something better. And so in order to deal with this, we have to figure out what we want to accomplish here. So what happens if there is a particle that has a mass that's greater than 0 at any of these vertices? So we're going to, again, look at these 3 different things, the mass, the shape, and the substructure, to exploit these differences so we can actually do this. Just to show you this graphically, what happens if you look at a top jet versus a light flavored jet, and you look at the mass of that jet as a function of the PT of that jet, they're getting more and more boosted, right? So because of the top quark, if you look back to this slide here, the top quark will have, nominally 3 centers of activity, W to QQ and the beep quark, whereas the light quark jets will just have, mostly 1, occasionally 1 or possibly 2. So as you increase the energy of the original top quark, let's say, You start off with a QCD jet that's just generated by QCD because this is the mass of the leading jet in the event. As you pass the W mass threshold, you often get one of the W's will get merged into one single jet. And then as you increase the energy even farther, then it gets merged even farther. So then the B comes in. So you start off with nothing, you add the W, and then you add the top quark. And as you increase the PT, it doesn't change much. If you contrast this with a light flavored jet, it will increase instead linearly, like I showed you up here. So if you remember back to this formula here in slide 2, it's linear, right? M is proportional to PT times R. So you have a discrimination here. So you have so you have something that is basically looking at a mass. So you can put a mass selection on this. If you say that you require that if you're just looking for top quarks, if you just look at the mass greater than 150, you can see there's not a whole lot of QCD that's up there. Okay. All right. So any questions so far on the sort of big picture? All right, so let's go into the first tool that we're going to be taking a look at, which is groomers. So prong finding and groomers kind of go hand in hand, so we're going to kind of tackle them more or less simultaneously. So we're going to go somewhat historically. The first groomer was the so-called the mass drop tagger, and that was followed by the Johns Hopkins tagger almost immediately following, which was used by CMS as the CMS top tagger. This mass drop tagger plus filtering was developed for Higgs to BB bar, and the Hopkins tagger was developed for top quark tagging. It turns out that this mass drop tagger was slightly modified and then to give some better theoretical behavior, and then it was generalized to the soft drop algorithm. And so we're going to talk about these in detail. And there's a couple of other algorithms that have been developed that we're going to look over. There's a bunch of other examples that I will probably not have time to get into because I want to get to quarks and gluons later. So, okay, the first one is the mass drop tagger. So the mass drop tagger was the first groomer that came on the market. So my citation somehow got cut off. Sorry about that. But all the citations are in the textbook that I showed you yesterday. So if you have some Higgs to BB bar, so the Higgs is coming here, and you have 2 B quarks, and you have a nice big jet that is encapsulating them all. Maybe there's radiation that is occurring off of the B jet or something. If you look at the mass drop, it tries to calculate 2 separate jets that will capture the different radiation profiles, and then do that recursively. So if you have a third radiation profile, you may have a jet that's kind of a subjet that's inside of this jet that is kind of lower in PT. It turns out that also lower in mass. So the way that you do this is that you cluster your jets with anti-KT or whatever, and then you recluster everything with the Cambridge-Aachen algorithm, and then you take one step away from the final jet. And then you check this criteria to see if the maximum of the 2 masses that you accomplish are less than some fraction times the sum of their masses. So you have a parameter here that's mu cut. And you also check that this splitting is symmetric. You don't want one big heavy thing and one tiny little, appendix that's sitting there. You really want it to be kind of symmetric in your kinematics. And so there's another parameter for that as well. So that's the difference between the minimum of their mass times the delta R between them has to be larger than some threshold times the sum of their four momentum sums mass. So if either of those things will fail, the least massive of I and J is discarded, and then you repeat the procedure. This gives you it will make sure that you're getting rid of the events where you have like a one big strong core and then a tiny little radiation. It just drops that radiation and just keeps the strong core. And so what it's trying to do is look at 2 strong cores versus 1 strong core. Okay, so you can either use this as a tagger for Higgs to BB bar, or you can actually use this as a groomer, which is known as filtering. Unfortunately, it turned out that if you follow the most massive branch of these clusterings, it often led to pathological situations. So at some point, they realized that if you switch to the highest PT instead of the highest mass, those pathologies went away. And it had considerably better theoretical behavior. So it had the similar analytic behavior, but much less sensitivity to non-perturbative corrections, which kind of I'm not going to go into it too much because it's really challenging to get to, but I will highlight a few areas where resummation and then non-perturbative effects are important. What they did instead is that they created this modified mass drop tagger, but it's really a momentum drop. So instead of the most massive branch, they follow the strongest PT branch. Okay, and that actually works better. It turns out that this can then be generalized to the soft drop algorithm, which is now a PT drop in a more rigorous sense. And this is known as the soft drop condition. So you take the minimum of the PTs of your final step of your unclustering, and you divide by the total sum, and that has to be greater than some parameter z cut times the angular distance between them, scaled by the r parameter that you're picking. And you can have an exponentiation of the generalization is that you can change this beta. So the modified mass drop tagger has beta is equal to 0, but the generalization is called the soft drop algorithm, and it's called soft drop because it drops the soft emissions. So yeah, here my references reappeared. Sorry about that. In order to understand what's happening there, we're going to introduce something called the Lund plane. So the Lund plane is if you look at a single radiation, so you have a progenitor quark that emits a gluon. You have, so I told you about Z and theta, right? Z is the fraction of this gluon, and then theta is this angle. And so if you plot that and you look at the logarithm of 1 over Z versus the logarithm of 1 over theta scaled by this R parameter, that's the Lund plane. So this is a phase space diagram of a single emission, okay? And the soft drop condition basically draws lines in this phase space, and you eliminate some portion of that phase space in your integral. So this is what this is doing. So if you look at this, this direction going upwards is softer and softer as you get closer to 0. So you get the logarithm of 1 over Z goes to 0. So you're getting harder and harder emissions. And if you're going to the right, it's more collinear, and going to the left, it's more wide angle separation. So if you look over here, this is sort of a large emission that's at higher energy and larger angle. But if you look at over here, the soft and collinear regime is where you look at a lot of soft gluon radiation that's collinear to the jet. That's the radiation we don't really care so much about, right? If it just emits a little wink, you lose a quarter. If you have $1 million and you lose a quarter, you don't really care so much, right? But if you have $1 million and you lose $500,000, that's where we're talking about. But we're looking to get rid of all of these sort of soft collinear radiations, and that's what it actually ends up doing. If you set beta is equal to 0, it just draws a horizontal line here, right? It does not pay attention to the momentum at all, and so it's just after some Z cut, it just eliminates everything above this line. And you can adjust beta, and it adjusts the slope of that line. You can keep more or less of the radiation as you want. And so that can be utilized to get rid of anything that you're not quite interested in. And what that does is pushes your mass peak further down to the left. So I showed you this picture, which is the differential cross section as a function of the ungroomed jet mass. And you see the Sudakov peak. So there is a suppression of this 1 over m behavior because of the phase space. If you groom away all of those soft gluons that you're resumming, the Sudakov peak goes away. Okay, and so then you're just left with something that's sort of just exponentially decaying, which is great. That's kind of what you want, right? We are looking at the hard radiation. We want to look at the distinguishing factor. We don't care if it's a tiny little rinky-dink thing over down here. We want to see large splittings because Higgs to BB bar has a large splitting. And so if we want to discriminate against QCD jets, you can see that this really, really suppresses the mass. So if you wanted to say tag a W boson with an ungroomed mass, the W boson lives here, right at the peak. That's not great. But if you wanted to look at it here, you can do it. Right. So this allows you to have that accessibility, and you can use the mass as the most important variable to discriminate between soft QCD or not soft QCD, light QCD versus heavy decays. So what this kind of looks like, if you look at your clustering, we have our final jet, and what we're going to do is undo that clustering. So we reverse our clustering sequence, and the way that this, we have the additional criteria of the soft drop criteria, okay? So you will do a soft drop, and then you'll have two subjets that you're doing. So because we're doing this in reverse, right? So we go, all of the algorithms have 1 to 2 splittings, and now we're reversing them. So it's 1 to 2, right? So here we are. And now you can see this is a simulation of a Higgs jet that is in the eta phi space with a calorimeter plot here. And you can see the clear two peaks here of the energy. So this is a single Higgs to BB bar jet, which has a radius of 1. And if you undo the clustering, you can get if you do this with Cambridge-Aachen, the last step will be combining these two pieces. Okay, so if you undo that step of clustering, you're already being able to distinguish between this, and you can now sum them out. If you then apply the grooming criteria, what it does is reduce, if you can kind of look around here, there's still a bunch of crap that's within these two subjects. But if you groom away all of that crap, it just goes away. And you just say, aha, here I have my 2 prongs that are left over, and I have a little bit left over here that's a kind of a, weaker part, but obviously that doesn't play a big role here. And you can just get rid of it in order to do this. And now you can work with these 2 separate subjects individually. And so you now have the Higgs to BB bar. You have a subjet that is corresponding to each BB bar pair, and pretty much nothing else, which is really quite amazing. There's a lot of algorithms that are discussed in the textbook that I linked to you. There's filtering, which I already covered. There's also pruning and trimming. I'm actually gonna skip it in the interest of time because, but there are there's a lot of history here and a lot of utility. Trimming, if I'll just go give you the broad picture, is that trimming reclusters with small r and removes soft subjects with after the clustering, which is kind of what soft drop does, but a little less theoretically controlled, so has some disadvantages. Filtering keeps the end hardest subjects, and pruning will try to undo the clustering to remove soft angle and large angle constituents in the clustering, so it doesn't do a pre-clustering step. That being said, they're all useful and can be utilized for with the Lund plane. The reason why these end up being complicated, you can take a look at the Lund plane and see what gets excluded by these algorithms. I'm gonna work from right to left. The modified mass drop algorithm has a nice, easy phase space to check, right? So there's a nice line here. The way that you read this is that this red line is a line of constant mass, and you're looking at the phase space, and this gets excluded, and you can easily exclude these with, these are nice trapezoidal pieces. The pruning and trimming are all basically doing the same thing, except they have more parameters. And so you have these little bits and pieces that you have to take into account. And so it does end up sculpting the mass distribution a little bit. So they're also a little challenging to calculate theoretically. There's also the CMS top tagger decomposition, which is similar to the Hopkins tagger, but I'm going to skip this one also. It's basically almost exactly the same kind of principle, except it does it. We're looking for 3 prongs instead of 2. And so you undo 2 steps of the clustering algorithm instead of 1 step. But I'm not going to go into the details of that one for the interest of time. So analytically, we can actually look at what is happening to these jet mass, to the jet mass variable. So if I look at now the variable called rho, which is the m over pt. So because of the linear scaling, we're going to look at a variable that takes out that linear scaling. So this is more of a dimensionless mass for calculations, which ends up being a lot easier to deal with because obviously the pt dependence is removed. So this variable has a similar structure to the mass, but it's then scaled by the pt. And this is the fractional differential cross section. So this is the shape. Now, okay. So if you look at the plane jet mass, it's here in red. You can see the clear Sudakov peak here. So all the jets, as the mass gets large, that means that you're broadening this out, and it's dominated by one single hard gluon emission. Everything keeps those. That's not what we want to groom away. Hard wide angle emissions we want to keep. And so that's what's happening as you get closer and closer to 2 jets, right? It starts off together, and it starts separating it out as you get higher and higher mass, and then it just becomes 2 jets. Okay. As you lower the mass, you're starting with something that's wide, and you're getting narrower and narrower. And that means you have to resum a bunch of soft gluons in order for it to make sense. Okay. And that's what's happening in the red distribution. So it starts off linear, more or less, and then it turns over as you resum all the gluons, and then it goes, and the phase space gets so suppressed that it goes to 0. The mass drop tagger has a very nice behavior above this cut here, which is the Z cut. It's exactly the same as the ungroomed mass, which is the same for all of them. But if you go below that, then it just suppresses the Sudakov peak very linearly, all the way down to 10 to the minus 6 or something. So this is why we really kind of like this behavior. It's extremely well theoretically controlled, and has a nice suppression of the Sudakov behavior and gets rid of all those soft gluons. You can change how much of that you keep with the soft drop algorithm. If you change beta equals 0 to beta equals 2, you can keep more of the Sudakov peak if you wanted it, for whatever reasons. I've also added the trimming and pruning and Y pruning and a bunch of other ones just to show you that they kind of all behave the same as the mass drop tagger for kind of moderate masses. But then if you get very, very, very low in mass, they start they're not quite as good at suppressing the Sudakov peak. So some soft radiation kind of sneaks back into the jet. But overall, this gives you, I don't know why this got off-centered, sorry. But overall, this gives you suppression of the Sudakov peak very nicely. Okay. So that's really what we're going to be looking at, is using that jet mass. Okay. So are there questions on this before I get into how to use this stuff? Yes. No. No. It's not a problem. You can still calculate this all theoretically. It's all very well controlled. Even the kink. I mean, you have to do 2 parts of the integral, right? You have a kink, so you have to do the left and the right, but the left is a box and the right is the jet mass, is a triangle. So it's actually pretty easy to do this calculation. I've even done this calculation myself. Well, so I just copied somebody else, of course, but even experimentalists can follow along with that calculation. It's not hard. Any other questions? Okay. So I'm going to go through some applications here. So again, so the first thing that we need to remember is that because we have a measurement, there's going to be some resolution. So we have a lot of, so the jets have uncertainties that I showed you somewhat yesterday. You can get now, but now you have 2 things you have to worry about: the energy resolution and also this angular resolution in between these. So you can get a lot of uncertainties. You get uncertainty from the measurement of the energy itself. You also get uncertainty from the number of particles. If you drop a particle, that's not great for grooming because it's like, I was hoping to use that. So if you have a track that goes into a calorimeter crack or something, that can screw up your algorithm a little bit. And you also get a little bit of uncertainty from the resolution of your angular measurement, which is also important. So putting that all together, there is a bit of a challenge because there are very few handles that have a mass that is specific or well known, right? If you're looking at jets, you can look at a photon, which is well measured, and you can have it back to back with another jet, and you can have a reference for your PT. So the photon balanced against the jet can get you an accurate measure of the jet's energy, and you can use that for calibration, which is what we do. If I had time, I would give you a full experimental overview of that, but we don't have that for mass. And so instead, what we usually do is use some particle that's in the standard model, of course. So it's a W or a top quark, because you can have very pure samples of W's or top quark. So if you look at a TT bar sample and look at the mass, a massive jet at sort of moderate PT, you can pick out the W boson that's in the TT bar events. So if you use that, you can see this is the mass of the W jet distribution, and you can see a clear W peak, and you can fit that to the data in the Monte Carlo, and you can get scale factors and see where this goes. And you can also look at this for fully boosted top quarks, and you can see that the top quark mass peak right here. So you can use this to calibrate these. Obviously, you can't do this for very, very high energies, right? Because this is all in the standard model bulk, which is kind of where we live for everything, right? So it has to be around the order of 100 GeV. And after that, you're kind of out of luck. But we do our best to do our extrapolations, and we kind of, we can manage how this goes about doing stuff. One of the other more challenging parts here is assessing performance. And all of these algorithms I showed you come with parameter choices, right? The Z-cut or beta or all these kinds of things. And the best one really kind of depends on what you want to do. And a lot of people can say, well, I have a really pure sample already. I don't really need to reject a lot of background. Whereas somebody else will say, my background is the size of Mount Everest, and I need to get rid of as much of it as humanly possible. So it depends on what you're actually looking at. And the best one depends on what you want to do, right? Think about your own experience. So if you say you have a 10% chance of failing, if you're playing poker, that's as good as it gets, man. Go all in. Push. That is it. You have a full house, and you're just betting that somebody doesn't have 4 of a kind, right? Or a higher full house. In healthcare, on the other hand, that's very, very troubling. If you had a 10% chance of dying today, everybody should be in the emergency room right now. Right? That is terrifying odds. Okay. So it really depends on what you're looking at. Probabilities are subjective. So we're going to talk about a couple of key concepts that I think are probably useful regardless, and it's even kind of more general than the boosted and grooming stuff that we've been looking at. We're going to have a few concepts to define: signal, which is what we want to select, and background, which is what we want to reject. There's 2 quantities that you need to know about. One is the efficiency, is how often you get the right answer, and the purity is how effective you are at rejecting the wrong one, right? So you want something that has as best efficiency as you can for the purity that you're given, okay? These are in tension, right? If you accept everything, it has 100% efficiency, but the purity is tiny, so you wouldn't want to do that, right? If you reject nothing, or if you accept nothing, then you're rejecting everything. So your purity is you're very pure, but it's 0 over 0, so it's kind of undefined, right? So you need to do this in tension. So these are often represented by something called the receiver operating characteristic curve, or a ROC curve. This is from basically ham radio for a long time ago, for signal to background stuff from radio operators in World War II. You'll see a very large number of plots about this in your career. So you have usually some measure of the efficiency on one axis, and some measure of the purity on the other axis. In this case, it's the background efficiency. And then better is low background efficiency and high signal efficiency. However, the axes often change. It's often 1 over the background efficiency, so purity or something. Just pay attention to which it is. And usually, if they know what they're doing, they'll tell you which is the direction that's good. So it's either to the bottom right or to the upper right, or somewhere, wherever you go. But what you're really looking at is to optimize this. And most of the time, for almost every algorithm that we have in the LHC, even in lepton ID, bottom quark tagging, top quark tagging, grooming, everything usually has some operating points that we pick along these curves. So we usually say, okay, so for somebody who needs very high purity, we'll go over here, and somebody who needs very high efficiency, we'll go over here, and somebody who's kind of in the middle, we'll pick something around here. Okay, so we often will give 2 or 3 operating points for all of the algorithms we do. And it's all just a question of, which one is better. It depends on which analysis you're doing, right? This also applies to leptons and everything else. So this is not just for boosted jets. Okay. So there are a lot of questions that you can address with jet substructure and all these tools. You can identify heavy hadronically decaying particles like Ws and tops. You could also even identify long-lived particles like B quarks. And you can then also do quark-initiated versus gluon-initiated jets, and I'm going to talk about this later. We're going to talk a little bit about this. This is extremely complicated, but I will just give you the vocabulary. I can't give you any details today. The tool is always dependent on the question you're looking to solve. So there's also another question of how sensitive that your algorithm ends up being. There is a lot of sensitivity to different effects. There can be detector effects rather. There can be the collider environment, in particular how much pileup you have, and also non-perturbative physics that is really, really challenging to get right and model. So there's also a question of robustness or resilience. And if you look at our textbook, they do have a nice description about this. So it is a reasonably good metric that you can do to quantify robustness or resilience. So they do that by looking at the uncertainty in the signal efficiency divided by the average value, and you add that to the uncertainty in the background efficiency divided by its average value squared, and you look at 1 over the square root of that whole quantity. And if they have an example of with or without the underlying event. Okay, so you look at the efficiency of the signal in the background without underlying event or with underlying event. And you can kind of quantify how large the effect is. It doesn't matter what effect you actually want to look at. You can turn, but typically you take some systematic effect, you turn it on and off, and you see how much this quantity has changed. Okay. And so I'm not going to go into the details of how this actually ends up working, but that is a metric that you can utilize to do this. But this ends up being very sensitive, very dependent on which tool that you're looking at and the environment you're interested in. Okay, but this is just a general metric. So, is there questions on assessing performance, ROC curves, stuff like that? This is challenging, but hopefully not too bad. Okay. Yes. Mm-hmm.
So it's done separately.
No, it is in the JET clustering, right? So you're taking the JET clustering algorithm. I showed you the plot yesterday, so where you can build this whole JET up. You get a whole dendrogram. If I can maybe even, do I dare? No, I don't dare. But it just looks at it has the clustering, and you start, it starts off like this, and you add going that direction, but then you undo the clustering. So you look at it backwards, and then you can, so it'll if you remember the dendrogram, maybe I'll just draw it on the chalkboard here. There is no spoon. Had my water bottle. Here we go. Thank you. All right. So, you have the dendrogram of, you have, a bunch of particles that are here. I merged these two first, and then I merged this two. Then I merge these. So what I'm doing is going this way. So I have a large split if I go this way. Right? And then I have another large split that's going this way, and then I have a small split that's going this way. So this would be like the B-jet. This would be like the W. All this together. Maybe this is just some little, if I looked at the quarks, the top quark, W, B. So we'll look at something maybe like this, and maybe one of these radiates. We don't care about that part. So maybe I eliminated that one. So now I have this hard jet, this hard jet, and this hard jet. And if these were at rest, these would be well separated throughout the detector, because it's not at rest. The particle is moving somewhere, and this splitting is what gives you that those two structures. And that's why it's very important. So this is why what I was saying yesterday, the Cambridge-Ockin algorithm is very good about this, because it's just looking at things that are close by, and it doesn't really care. KT also works, but Cambridge-Ockin works better. That answer your question? I hope so. Okay. Any other questions? All right. How much time do I have? About 15 minutes. So let's see how much time I'm going to get. Okay. So you know what? I'm going to skip a little bit of the measured values here. We can come back to them. And I'm going to come back to I'm going to talk about the jet shapes. So if I have time, I'm going to come back to the measurements, because they are cool, and you can see a lot of rich phenomenology, but I'm gonna skip it for now. I'm gonna go to the jet shapes just so I can make sure that I get to the quark-gluon discrimination, which is reliant on this. So we've been talking about the clustering, but it's also the case that these things have different shapes. And what that really means is, it's not just about, if you look at this picture again, it's not just a question of, the number. It's also their distribution of what it looks like within the jet. So, it could have different radiation profile, excuse me. So a generalized angularity is some product of the momentum fraction and the delta R between particles, right? So you have, if you have some jet and you have some particle that you're looking at, that particle has its momentum fraction relative to the jet, which is Z, and then the delta R. And the product of those two raised to some power can be whatever you want, right? You can pick kappa and beta depending on what observable you want. But a lot of observables can be written in this kind of expansion, including the jet mass. And they're at least proportional to that. This is dimensionless, but if you make it dimensionful, some of these angularities just become the jet mass. So this is the momentum fraction. So Z sub I is PT sub I over the sum of all the constituents in the jet. And then the angular distance of the jet axis is just the standard delta R difference here. Now, these are collinear unsafe. As we were talking about last night in the recitation, a lot of these kinds of, this was one of the questions that you looked at. This is not exactly an angularity, but it's related to an angularity. So anytime you're trying to sum over a bunch of different particles that are in there, unless kappa is equal to 1, it's collinear unsafe. If kappa is equal to 1, then it's collinear safe. And then you could take beta to different values. And if its beta is equal to 1, that's referred to as the width or the girth. It's just the product. If you have this kappa 1 and beta 1, it's just the product of Z sub I times delta R, right? So it's that's kind of how a weighted average of how far they are from the jet core. If you square it, beta squared, that's actually the jet mass, right? So the jet mass is is proportional to that times the energy of the jet. So it's omega would be if kappa is 1, it's just all the products of their momentum fractions times their angle. So it's Z times theta squared is the jet mass if you multiply it by E sub j. So mass is related to the special version of the angularity with kappa is equal to 1. Okay. So they're very closely related, as I mentioned earlier, and you can use one to play around with the other. But there's a bunch of other special cases that can happen. You can also set kappa is equal to 0 and beta is equal to 0. That's just the multiplicity. Okay, so that counts as an angularity. And you can set beta is equal to 2 and beta is equal to 0 and kappa equals to 2. That's known as PTD for those of you who are in quark-gluon land. So that is the dispersion of the momentum across the jet, let's say. And this is also useful in quark-gluon discrimination. A lot of these angularities are the only handles you have for quark-gluon discrimination in any substantive sense. One example of these angularities is so-called n-subjettiness, and that quantifies how many prongs the jet has. So the way that this happens is that you first define some set of axes. Now, I told you yesterday that defining axes ahead of time is usually a bad idea. However, these actually use axes that are sensible, usually from the jet itself, so it's just taking the axis that the jet made. So you're not arbitrarily setting these, but you do have different axis choices. So the variables here, so tau sub n can be raised to some power beta. It's the sum of PT of the constituents times the minimum of the delta R's to raise to some beta power. So it's related to the angularity, but instead of the momentum fraction, you're just looking at the momentum itself. So it's close, but not exactly the same thing. Beta is a free parameter. Oftentimes we set it to 1. You can have different choices depending on what you actually want to do. And you can also use different axis choices. So usually we use the KT algorithm and pick the n-exclusive subjects to use that as the axes. You can also use the generalized KT algorithm, which you can just pick a different value of beta. And you can also, so you can match the power of beta that you wanted, or you can pick the so-called winner-take-all scheme, where you just pick the hardest one in the jet, and that becomes the axis. You can also use the minimal axis, where you minimize this quantity to get it, and it's kind of like that would be similar to the k-means algorithm that we talked about yesterday a little bit. And you can also just do this with one path. So there's lots of axis choices that you can do. I don't want to get into them, but at the end of the day, what you have to remember is these are trying to just measure how much stuff is inside of the jet and where it lives. A lot of times the n-subjettiness is done in ratios. So you're looking at the ratio of n subjects versus m subjects, where it's usually n to n minus 1. So you're looking at the ratio of the 3 subjettiness to the 2 subjettiness. And that gives you good discrimination for 3-prong structure. And if you look at 2-prong structure, it's 2 subjettiness over 1 subjettiness. And this gives you very strong handles for discrimination of that too. But I still need to go a little bit faster. So I'm going to try to wrap this up as quickly as I can. The energy correlation functions are similar to n-subjettiness, but we don't have a reference axis, which is nice. and it goes into these generalized angularities. But you can also do this now with correlations of the energy and angulars and angles. So you can do a 2-point correlation. So you take all the pairs. You can do a 3-point correlation where you take all the triplets. As you can expect, this gets much more computationally intensive the farther down you go. But it also gives you more information the farther down you go. So you can do all sorts of things with these. Most of the time, we're just looking at E2 or E3, because after that, it gets computationally intractable to do anything of practical value in finite time. So again, but it's a similar kind of quantity where you're just weighting the energy that's inside of the jet by their momentum fraction and their angle, and to see how that works. And you could also generalize this. There's all sorts of ways to go about this with different beta values, and so you can do this very, very to your heart's content with increasing amount of complexity. But all these variables just give you kind of a different, like you can almost think of them as a convolutional kernel, like a convolutional neural network. You're kind of looking at how 3-prongy it is, how 2-prongy it is, how frequently does the 2-prong come with a fraction of a half or versus fraction of a third. All sorts of things that you can do with these, and they're closely related. And I could give a lot more detail on this, but I will not. I'm going to skip this. So generally speaking, it's very advantageous to combine the tools together, and that's ultimately what builds into sort of neural network approaches. So you start slapping all these things into a giant neural network or boosted decision tree, and you can start building up discrimination power from there, and it'll use all these to build a numerical discriminator on top of all these physics-based discriminators. Or you can just have a deep neural network just try to kind of guess all of these things, which it can do. It actually learns. It can learn a lot of these things in and of themselves. That being said, you lose the understandableness of being a human. If the robot just tells you, "Oh, look, I think there's 2 subjects in there," and you say, "Why?" and it says, "I didn't know." I mean, because ones and zeros in machine learning space, and you'd be like, "Okay, I don't understand." But there's a lot of different options that both CMS and Atlas use, and other collaborations as well. But you staple these all together and we use them extensively now. I'm going to skip this part too because I only have 5 minutes and I want to get to the quarks versus gluons. Before I do that, are there any questions on the angularities briefly? All right, let's go to the quarks versus gluons. As you can see, the idea of a quark jet or a gluon jet is an ambiguous concept to begin with, okay? This is rooted in a perturbative language, right? However, QCD is not perturbative forever, right? As you get lower and lower in energy, the coupling constant becomes greater than 1. It becomes greater than 1 and it becomes non-perturbative, right? And that just means that you can't look at it as a single particle anymore. It is the quantum field, like what we were talking about yesterday with the quark C, right? So if you just look at the simplest case of, let's say, a Z production with a jet, and you have the Z go to neutrinos, so the only thing that you have is the quark or the gluon jet. Depending on which part of the proton gets selected, it can either be a quark or a gluon, and then you'll have 1 gluon jet and 1 quark jet if you do this in the same event selection, right? If you require just 1 jet and some missing transverse energy, you can get some events that look like both of these, and there'll be some of these and some of these. The problem is that there is now also radiation in and outside of the jet. You also get resummation, and you get non-perturbative effects. So the idea of a quark jet or a gluon jet is ill-defined from the beginning. It is rooted in our misunderstanding of quantum field theory that is entirely perturbative, right? It assumes everything is perturbative, and that language of quark or gluon jet is a fundamentally ill-defined concept. What we can say is that we're moving from the idea as a quark as a noun to a quark as an adjective. So this is a quark jet versus this region is quark enriched. Are different statements. The first one is wrong. The second one is correct. Something that is enriched in quarks would be that if you're selecting more like this versus this. So what you really need to do is have event selections that are quark or gluon enriched. So there's a whole lot of context of what this actually means. that what we're actually talking about this, what is a quark jet? There's varying levels of being defined. A quark parton means nothing. It is dependent entirely on your Monte Carlo model and the perturbative approximation that we're doing. That doesn't really exist in nature. So this is meaningless. A Born level quark parton. Okay, yes, it makes sense in a calculation, but still doesn't really make any sense. You could also have an initiating quark parton in a final state shower. Well, kind of makes a little bit more sense. As you keep getting farther and farther down, you get less and less like a noun and more like an adjective, right? It's very defined to say we have a phase space region that yields an enhanced sample of quarks. Okay. Quark as noun is usually good enough for many analyses, but you have to realize that it is strongly limited by the strong interaction. Right? It is not a very well-defined concept, and you have to be careful about what you say and where, because you can get into meaningless statements pretty fast. But this is really what we're talking about when we're looking at analyses. One of my graduate student is looking at the difference between jet masses in quark-enriched and gluon-enriched samples. And so the quark-enriched samples are dijets, and the gluon-enriched, the quark-enriched samples are Z plus jets, and the gluon-enriched samples can be a mixture of dijets and also trijets. So they will have different quark-gluon admixtures. As you're looking at more electroweak kinds of things, quark jet becomes a little bit more meaningful because you have a color singlet somewhere in the event. And so you can this gets more enhanced. It gets closer to a noun than it is to an adjective. It gets closer to a noun than a dijet event, let's say. But it's still not quite meaningful, right? Because these get dressed with lots of gluons, and you can have all sorts of radiation that's happening. Okay. So there's only a few handles to discriminate between these because it's ultimately the same dynamics. The only difference is that the gluons have a higher color charge. And so what that means is that as it progresses, it will typically radiate more. So that will lead to a broader jet with a higher mass and also has higher multiplicity. So those are the only handles that you really have. And so what you need to do is use these angularity variables and substructure variables that I was talking about earlier, but none of them are perfect. You get, 60, 70% regions. So if you're looking into the handles, like if you're looking at these cases, in Monte Carlo, what are the textbook that we're looking at, this is the events that they generate. So you can generate Z plus gluon, where the Z goes to nu, or a Z plus quark, where the Z goes to nu, and then you have a really enriched gluon sample versus a really enriched quark sample, and you can look at the differences in Monte Carlo predictions. It's helpful to look at the angularity variables that we looked at earlier. But that's really basically all we can kind of do. Oh, I lost a slide. Where'd it go? Hold on a second. I'll get it back. I think it's lecture 9. Nope, lecture 8. I lied. Here we go. A lot of analytic behavior. Okay, so you can, I'm just going to show you the plot. So here we are. So this is the generalized angularity for different values for the quark and gluon enriched. So you can see these are just different angularity variables that I talked about earlier. These are all different things that are stapled on top of each other with different alpha values for soft drop, different beta values in soft drop, and you can see that there is some discrimination between the quark and gluon, which is solid versus dashed, but it's not terribly good. Right? You're comparing this black to this black, and if you drew a cut here, your purity would be 30%, kind of as good as it gets. So you're not. So what we do have is that once you staple all these things together, this is where machine learning can really come into play. So normally what ends up happening is you sweep these all into your giant machine learning thing, and you stir this around until an answer comes out, and then you're good to go. But at the end of the day, there's not a terribly strong separation between them. Okay, so looking at quark versus what happened to my? Oh no, that's not. Shoot. Sorry. So depending on where you live, what you want to do with this, that ends up being the only thing that you really have. I'm kind of out of time, but I will just glance at some measured values here of quark versus gluons. So you can see that this is the ungroomed mass in quark versus gluons. So you can see this is the mass in different PT bins. Bless you. And this is the shape as a stacked plot. So these are all multiplied by some factor. And you can see the quark versus gluons. The dijet events tends to be broader. The peak here at, if you pick, say 200, the peak here is at like 50. And if you pick 200 here, the peak is a little bit lower than that. So it's at like 40. So it's very, very, very tiny differences, but it's not, they are manageable. Okay, I'm out of time. So are there any questions? Sorry, I had to skip a little bit. All right, that's all I got.
Great talk with you for another half an hour. Discuss all details. I have a couple of questions.
Yes.
A few years ago, there was this beautiful idea by Jan